Hi, I hope your family and you guys are all healthy. Your Algebra 2 teachers miss you a lot. Today we're going to be focusing in on Chapter 24, Section 2 over exponential equations. And if you recall, last week we were solving exponential equations also, but see if you can remember what method we used to solve them. Good. So we would have used this idea that a to the m equals a to the n, or two sides of an equation with the same base mean that the exponents must be the same thing. And that's how we solved all our equations. And our method was that we were going to get our bases the same and then we could cancel them out and set the exponents equal. So what happens, do you think, if we can't get two bases that are the same on either side? Well, this is where another method comes in that I mentioned on the last video that we were talking about this solving of exponential equations. We use logarithms and natural logarithms. So today we're going to dive into that. But before that, I want to take us back to even some of us before pre-algebra, where we first started working with equations, specifically linear equations. So take a look at that 6n plus 7 equals 2n plus 5. How would we solve that? What steps would we take? And as you're solving that, I'd like you to be solving it on your sheet, and I'll solve it on the screen also so you can kind of check your work. But think about why you're doing what you're doing and why you're choosing the numbers that you're moving to the other side. So let's go ahead and get started. Then I'm going to move my 5 over. Minus 6. 2 equals negative 4n. Then we're going to divide, of course, so our n is going to come to negative 1/2 when we simplify. Now, what did we notice our steps were? I started with my 5, but you could have also subtracted over your 7. And this 7 and 5 have a specific name. We call those constants, like we mentioned in the earlier video. And the name of the number that's attached to our variable is called a coefficient. So you'll see that what we're trying to do is get rid of constants and coefficients to isolate the n. We're trying to get all the n terms combined and over to one side. So we can say, what step did you take? We moved constants and coefficients to isolate the variable. And how specifically did we do that? Why did I subtract here? Well, of course, because I had addition. And over here, we saw that we subtracted because this term is positive. And then when we were working with getting this 4 away from the n, we divided. So we're doing the opposite operation. So for example, when we're doing addition, we're going to do subtraction. And when we're doing multiplication, we're going to divide. And you have worked with more of these. What about if I have a squared term? What do? We take the square root. So you have all these different techniques in your toolbox depending on what operations you see within your equation. Well, today we're just adding one more to that toolbox. And that concept is, what do we do with logarithms? What's the inverse operation of logarithms? So I'd like you to try and type something in your calculator for me. Type log base 10, 10 to the first. What do you get? Good, you get 1. Okay, is the pattern consistent? What if we do log base 3, 3 to the first? What do we get? 1. So our pattern is consistent. Our logarithms are always undoing our exponents that we see. They're going to give us the exponent. So we're just going to use that same exact concept when we're solving these equations. So we can say a logarithm is the inverse of exponential functions. And we notice up here I use 2 arrows, which means if I have addition, I can subtract to get it to cancel, or if I have a negative term, I can add to get it to cancel. The same thing holds here. The log is the inverse for an exponential function, and an exponential function is the inverse of a log. So the bidirectional nature that we see in all other areas in our operations that we've seen before still is consistent here. So let's try it out and see if we understand how it works. If I have 24 to the x power equals 7, I'm not having to deal with any coefficients out in front here or any constants on the back end of our left side. So I can just start with a log. And I'm going to say the log of base 24 and 24 to the x power equals, and if we look back at our work that we just did over on this side of our screen, we see that what we did to one side, we also had to do to the other. And the same holds true for our logarithms. I'm going to still have to take the log base 24 of my 7 just to keep everything balanced on my equation. I'm going to say log base 24 of 7. And then we can cancel these out because, as we said, they're inverse operations. So this becomes x equals log base 24 of 7. Now, we have another way that we can represent this base 24. And the way that we do that is through a fraction. And we're going to take the big log over the small number. So it'll become log of 7 over log of 24. Now, can you type that in your calculator for me? Make sure you're putting parentheses at the end and beginning of your log 7 and then the division symbol and then another set of parentheses for me. When you do that, you should get right about 0.612. Now, it's important to note you cannot round during this process. You always round at the very end, and the reason for that is just to make sure on assessments and quizzes we're all getting about the same answer. And if we round partway through, it's going to mess up our answer, and you won't get it right on a test and a quiz. So just make sure you're waiting until the very end. If we look at our equal sign as opposed to this sign, they're a little bit different. The squiggly equals, as its non-technical term, actually means approximate. So when you see this squiggly equals, that just says this is really close to the answer but isn't quite the answer. So that's why we have to use them in this case, because we aren't writing out our whole entire decimal. Okay, we can circle that. Now let's move on to number 2. Again, there's no coefficient out front, and there's no constant that's in the larger term, not in the exponent. So we're going to do the same thing, take a log. And what I do to one side, I'm going to do to the other. So we're going to take log base 6 of 250 equals log base 6 of our 6 to the x minus 2 power. Now, because they're inverse operations, we can cancel these, and it's going to become x minus 2 equals log 6 250. Okay, now just like we would in any equation, we want to get this x alone. So I'm going to go ahead and move this 2 to the other side by using addition just like we would any other time. Cancel. And I'm going to put it in fraction form again so it's easier for you guys to type in your calculator. Plus our 2 equals our x. Go ahead and type that in and see what you get. You should get approximately 5.082. And now if we look at number 3, what's different between this number 3, the 1, and the 2? Good, we have a constant now. So just like we did in the very beginning when we tried our early linear equation to solve, we took care of these constants first. They were the first things that we got out of the way. So we're going to stay with that pattern and get the 7 out of the way so we can use our logarithm. So I'm going to subtract our 7 over, subtract our 7, and it becomes 54 equals 8 to the 4x. Well, now I don't have anything else in my way, so I can take that logarithm on this side and this side. So we'll say log base 8 of 8 4x equals log 8 of 54. And our log and our base are going to cancel. So this is going to become 4x equals, and again, I'm going to flip it to fraction form, so our big number is on the top and our little is on the bottom. So log of 54 over log of 8. We're going to divide by 4. And when I do that, we're just going to add it to the denominator here. So type that in your calculator. Make sure you're putting parentheses around here using your division symbol and parentheses around there. You should get, if you typed it in correctly, that x is approximately 0.480. If you got something a little bit off, look through my work and compare it to your work and see if you might have a funny mistake somewhere along the way. And then let's look at number 4. What's the major difference now? There are 2 big differences that I see. What are they? The main one is that now we have an e, plus we have a 50 attached to that base. So just like over here, we got rid of that coefficient by dividing this 4 over and dividing this 4 over here. We're going to do that same exact thing on our exponential functions. So I'm going to divide my 50. What I do to one side, I have to do to the other. Divide by 50, and that gives us 12 equals e to the x minus 3. Now, what is the name and what is the abbreviation of the logarithm with base e? It has a special name and a different abbreviation that we're used to. It's called the natural logarithm. So I'm going to say ln is its abbreviation, e to the x minus 3 equals ln 12. And these are going to cancel out just like they do in regular logs. And this will become x minus 3 equals the natural log of 12. And I want to get this 3 out of the way, so my x is all by itself on that side. So I'm going to add it over. And what do you get when you type that into the calculator? You should get approximately 5.485. If you have any questions over these notes or the homework or any concepts in general from the past couple of weeks, feel free to stop by our office hours. I hope you and your family stay healthy.